For this problem, we're going to solve the number of photons that are needed. What are we doing with them? Well, I have some water, about 1/4 of a liter, so a nice cup of coffee or cocoa or something that I'm heating in my microwave. It starts at 25 Celsius and I'm bringing it up to 85.5. And my microwave has an IR emitter with photons length of 12.24 centimeters. Given this info, can you determine the total moles of photons that our water had to absorb? And how many photons per water molecule? Go ahead, pause, give this a try, and come on back. All right, if you're back, well, what's the first thing we got to do? Well, I'm heating my water. So think about the process here. I'm putting energy into my water using photons. I need to know how much energy I put in. So we need to find energy of the water. Once I know the energy of the water, I also need to find the energy of each photon. Because remember, photons of a wavelength have a set energy. So while the total of all my photons has to add up to the energy of water, each individual photon has a set energy. So I'll need to find these two so I can relate them. So step one, let's find that water. I've got water, it heats up, so Q equals ms delta T. I've got 237 grams of water, my S value for water, 4.184 joules per grams degrees Celsius, and a temp 85.5 minus 25.0 for 60.5. Our energy for the water, 59,992 joules. So I have my energy for my water. I need my energy for my photon. For that, the energy of a photon is going to be equal to hc over lambda. Well, we usually do lambda in meters because the speed of light is in meters. So I need to convert my centimeters. 12.24 centimeters, there's 100 centimeters in 1 meter, 0.1124 meters. So my H, Planck's constant, 6.626 times 10 to the negative 34 joules seconds. My speed of light, 3 times 10 to the 8 meters per second, all over 0.1129 meters. I'll be left just in joules. The energy for a single photon of this energy, 1.62 times 10 to negative 24 joules. Which, if we think about it, visible light tends to be the 10 to the minus 19 range, so this is quite a bit smaller, which makes sense for infrared. It's less energetic. So our calculation seems to be holding up. I now have the total energy, and I have the energy per photon, which means I can find total photons. I know there are 59,992 joules, and there's a ratio of 1.62 times 10 negative 24 joules in every 1 photon. 3.7 times 10 to the 28 photons. If we want that in moles, there's 6.022 times 10 to the 23 things in 1 mole, which will give us 61,495 moles of photons. Moles of photons. Remember how incredibly tiny a photon actually is in terms of energy. Like a mole of matter is an enormously large amount of matter, and yet we need a huge amount of moles of photons to interact with even a small amount of matter. Which was our next question. 237 grams of water. Well, there is 18.016 grams in every 1 mole. And 1 mole has 6.022 times 10 to the 23 molecules. So we can find out how many molecules of water there is, and we know the total number of photons. So there is 7.92 times 10 to the 24 H2O molecules. I have my photons, I have my molecules. How many photons per molecule? 3.7 times 10 to the 28 photons. 7.92 times 10 to the 24 H2O molecules for 4,674 photons per H2O. It takes a large amount of photons to heat up this water. We're not adding a significant amount of energy per photon. And so your microwave sits and it cranks away for a while, constantly generating photons, adding that energy. A good chunk of them never even make it into the water. They bounce around, heat up the air and things like that, escape the microwave. And so you realistically have to use much more than this to accomplish heating up your coffee or whatever. But here's how we can take an energy that we know needs to be put into a material and look at the photons we are using to add that energy in order to determine the amount of photons that were required.